This is a project to investigate the effectiveness of implementing neuroevolution in a variety of video games as an AI which can learn to play the game. Neuroevolution uses a combination of neural networks and genetic algorithms to learn to complete a task. A neural network will control an agent, which is one player of the game, by taking in information from the game and then deciding on an output for that frame. Neural networks work by taking inputs to a layer, multiplying each of these by different values, known as weights, then adding an extra value, known as a bias, and finally passing this value through an activation function. Otherwise, the whole network can only perform linear transformations on the inputs, making it much less versatile. This is done with different weights for however many outputs are wanted for that layer. This can then be repeated for each of the layers in the network. I'm calculating this through matrix multiplication, storing the weights for a layer in matrices so they can efficiently be multiplied for the whole layer. Initially, the neural network which controls an agent will be randomized, so will likely not be very effective. In order to learn, I will use a genetic algorithm to allow target behaviors to develop over time through evolution. The key stages of a genetic algorithm are initialization, fitness calculation, selection, crossover, and mutation. For the initialization step, the first generation of agents will have neural networks which will be initialized with random weights, which means they may have some good features, but overall are likely to not be very good at the given task. I will simulate a population of agents who will all have different neural networks and play the game at the same time. The individual agents will be awarded points as they play, which will contribute to their score. Once all the agents of a generation have died, they will each have a fitness calculated, which will be based off their score, and is a measure of how good they were at the task, and the fitness of the whole population will sum to 1. This is the fitness calculation. For the selection phase, I can create a new generation by randomly selecting parents from the previous generation, with those that performed better more likely to become parents. This will be done by selecting a random number from 0 to 1, and then going through each parent, removing their fitness score from this number until it reaches 0, which will make that parent the chosen parent for a child of the next generation. This means I'll be selecting a parent randomly, but in proportion to their fitness. This will be done twice for each child of the next generation. For crossover, I will take the two parents I have selected and choose a layer in their neural network to split it at. We can think of the neural networks as a function which takes in a series of inputs for a layer and calculates a series of outputs for that layer, which is repeated for however many layers the network has. In the case of my implementation for these games, 2 or 3 layers will be sufficient. The combined neural networks of the parents becomes the neural network of the child. This is repeated to create a population of children the same size as the current population. Finally, the mutation stage is vital as it allows the children to develop new behaviors which weren't present in the initial population. This means that over time, the children can mutate to learn to do something that none of their parents were capable of. The children's neural network will be mutated by randomly selecting weights of the neural network to mutate, and then adjusting them by adding a value from a normal distribution. The first game I implemented this for was Flappy Bird. First, I had to create the game, which I did using the Pygame module in Python. Now it was time to add the AI to control the game. I added my neural network library, which is what each bird will have as a brain to control it each frame. Then the genetic algorithm library, which, at the end of a generation, handle calculating the fitness and will return a new population of children. As the actions of any agent has no effect on the environment, only on its own movement, all the agents can be simulated at once in the same game. Finally, we need to define what each bird can see. To keep the network simple, each bird will be able to see its horizontal distance to the next pipe, the y distance to the top of the next pipe, the y distance to the bottom of the next pipe, and its y velocity. Its y velocity is vital, as the agent has no memory, so if it were in a situation like this, it wouldn't know if it had jumped the frame before, or whether it was travelling up or down. It will be rewarded by getting a point each frame it is alive, which I chose over just awarding points for each pipe a bird passes, as a bird which almost gets to a new pipe should get more points than one which crashes straight after going through one. Here we can see the first generation with random neural networks. Most members of the population fly straight off the screen and die, but some are able to maintain a more constant height. As we can see, after just a few generations, this AI has learnt to play Flappy Bird relatively well. The AI in this generation is able to survive for a long time. We can skip forward and see it is still going after 500 pipes. If we look at the neural network which is controlling this agent, we can see that the y velocity and distance to the top of the next pipe probably have the greatest effect on the bird's actions. Green lines show a positive connection, while red lines show a negative connection. As we can see, the agents are able to learn to play the game well after just a few generations, so I wanted to see how well they could do on a more complex scenario, such as learning to drive around a track. First, I created a car which could be controlled and a track. I needed a way to detect when the car collided with the edge of the track. As I would be simulating many cars at once, I needed a method which would not be too computationally intensive, so I decided to consider the car crashed if its centre was outside of the track. I did this by considering two polygons, the one which makes up the outside of the track and the one which makes up the inside of the track. As long as the car is inside the large polygon but outside the smaller polygon, it must be on the track. For each of these two polygons, to determine if the car was inside, I simulated a ray from the car to the side of the screen, then calculated the number of times this ray intersected the edge of the polygon. If this was an even number of times, the car must be outside the polygon, or if it is an odd number of times, the car must be inside. By checking this for both polygons, I could determine whether the car had crashed. I then added the AI to the cars, which meant I had to define what the cars could see and how they would be rewarded. To see, each car would shoot out 7 rays at different angles from the front of the car and calculate the distance until it hit a wall. I calculated this by solving whether the equations of each ray and each edge of the track intersected, and if so, how far away it was. This would make up the inputs for the network. As a reward, I placed reward circles around the track, and whenever a car entered one of these, it got a point. With the AI all set up, it was time to run it and see how it did. This looks impressive, but if we remove the track to see what the AI can see, with just this information, it is doing a really great job. As this AI is learning behaviours based on its environment, not just learning a sequence of moves, I could give it a different track and it should be able to drive successfully. As it had been successful at both challenges I had given it, I thought I would try to see how well this AI could do at playing a more complicated game, such as Asteroids. As usual, I first had to create the game. I spent a lot of time looking at information on the original game, such as the mechanics and the speed of different items, to make it as realistic as possible. I then added the AI, which meant I had to decide how to reward the AI and what it would be able to see. Similar to the car driving AI, in order to see, the agent would shoot 8 rays from the centre of the ship and measure the distance to where it hit an asteroid. I did this by solving the equation of each line intersecting with the circle which made up each asteroid, finding any solutions, and then finding the shortest one. The AI would get points as the player would in the original game, 20 for destroying a large asteroid, 50 for a medium one, and 100 for a small one. Initially, the best behaviour that AI quickly learns is to spin in circles, shooting constantly, which works reasonably well. Over time, the AI develops a behaviour where it spins until one of the rays intersects an asteroid nearby. It then rotates to face that asteroid and destroy it, before continuing to spin to find another one, which is quite an effective strategy. I have found neuroevolution to be an effective method to learn to play games. As an unsupervised type of learning, it is suitable for this application, as it does not require target outputs for each frame to train it, such as using backpropagation to train a neural network, which wouldn't have been possible in a situation like this. Instead, it is able to learn by gaining rewards when it carries out certain actions.